Today's topic is quantitative interpretation in a modern world. And as we all know, um, the machine learning algorithms and workflows have been helping us throughout our lives in many different aspects. And of course, we had to try it on QI, and we are getting amazing results. It's completely changing the way we do certain things. And I'll be showing you some basic introductions and get into some technical weeds, details, and then finally we'll share some lessons we learned doing this over multiple projects. The first part of my talk is going to be just a gentle introduction to QI and machine learning, and then we will look at advancements of our workflows using machine learning. And then, as I mentioned, we'll dive into technical details and finally summarize everything. Starting with conventional QI, as you all might be familiar with, there's a lot of forward modeling, rock physics, inverse theory, probability distributions, statistics of data, everything included in conventional QI. Some of these things are also transferable to machine learning methods, which I'll get into a little bit in future slides. And one of the most cumbersome parts of conventional inversions is background model building and extracting very stable wavelets. And our machine learning workflows completely eliminate that. And some of the methods I'll talk about in conventional QI, like stochastic methods, or some companies call them geostatistical inversion methods, they may require a lot of expertise and knowledge in the methods and the actual tools that they're using. If you do a deterministic reservoir characterization project, typical deliverables you'll get are like volumes of impedance or other rock properties, and then we could use cross-plotting methods and geobody generation methods to identify sweet spots and zones of interest. And in stochastic or geostatistical methods, mainly we get similar results to these. However, we also get uncertainty bars on our measurements, so we can do estimates of our reserves, etc., with more confidence and adjust our risk tolerance based on that. Here's some more details about how conventional inversion methods are done. I'll just go through the main titles where in deterministic methods, as I mentioned, we use wells, well ties, angle stacks, and wavelets, and there are some methods that also make use of azimuthal seismic data to extract some fracturing attributes, etc. However, for each of these methods, you almost always have to build background models, and typical methods for that are either extrapolation with inverse distance, or kriging, or co-kriging with seismic velocities, etc. And most of these algorithms utilize a model-based optimization algorithm. Some of them are Bayesian, some of them are frequentist algorithms. And finally, once we relate the seismic to rock properties that fit our models, we can compute more elastic parameters and interpret them. And stochastic methods, in addition to these, include prior information to guide the result. And there are some methods that can switch models based on facies. And most of these methods use Bayesian inference methods. Some very advanced methods are using Markov chain Monte Carlo methods, which are very powerful but very difficult to use and time consuming. The advantages are much higher resolution compared to deterministic inversions, and we could get multiple realizations out, and uncertainty is quantified, and we have probabilities of our rock properties. The disadvantages are, as I mentioned before, and I can't stress this enough, it requires a high level of expertise in tools and workflow, and not everybody has that much experience to be able to use these kind of tools. And sometimes they're very time consuming. From experience, most geostatistical inversion projects can take anywhere from 4 to 6 months, and I just put in 5+ months for average here. And it may not be always trivial to collect all the prior information, all the histograms, all the rock property distributions, etc., and putting them in the right format, putting for our inversion algorithms could be a very cumbersome task. And some methods also require multiple background models, which you have to make background models per facies, which ultimately gets used in that model switching per facies steps. And now I'll give a brief introduction of machine learning. We have had a couple webinars about this. My colleagues presented a lot of technical details about what machine learning is, what it does, what's the goal. I'm just going to go through some high-level details here for people who haven't seen our previous webinars. So there's a lot of confusion between what AI and machine learning is. Some people use it interchangeably and some people don't, but the correct thing is machine learning is a subset of artificial intelligence where we teach machines to do some tasks without explicitly programming them. And one of the most popular methods of machine learning is deep learning. This is mainly used in our phones, image processing, all sorts of things, and it is a subset of the machine learning workflows. Here's a long definition of machine learning if anybody wants to read it. As I mentioned, we are trying to perform tasks without explicitly programming computers. And you can split machine learning methods into supervised and unsupervised learning methods. Generally, there's more like reinforcement learning, etc., which is used in self-driving cars. Supervised and unsupervised learning means basically we're telling the computer, hey, this is a fault. Try to find measurements that explain this fault. That's supervised. And unsupervised means we're not telling the computer anything. It's trying to find patterns in our data by itself. And all of these methods are closely related to or include a lot of statistics, data mining, pattern recognition, and mathematical optimization. And here are some examples of methods that are currently utilized in machine learning. And the most popular ones are neural networks, support vector machines, and we have been actually using generalized linear models for a very long time in our discipline. And the advantages of machine learning methods are they're very powerful. They have very high prediction power, and they can sometimes see relationships that we are approximating that are not really explained well in our models. And they can also look at multidimensional data much better than we can, and also it can find relationships between data that's not really closely related that would be very difficult for us to do. And of course, machine learning isn't just the holy grail of everything. There are some challenges. First of all, we need to define our problem correctly, and that requires domain expertise. Like if we went to a computer scientist and said like, hey, invent seismic inversion and walk away, they won't be able to do anything in a timely manner. So our domain expertise comes in here where we explain the problem and what we look for, what we need, what we want to see from the data, and that's how we can choose what algorithm to use, what kind of data environment we're going to use, etc. And another challenge could be sparse or limited data. Machine learning methods usually require a lot of data to learn. However, there are very powerful methods that allow us to do these data-hungry algorithms on conventional data sets, like sparse limited data sets like we would have in a seismic inversion setting. And we've had success with using maybe 3-4 wells for doing a neural network-based seismic inversion method. And typically that's how many wells we get on a conventional inversion. Maybe it's even more. And one more thing we need to do is if we don't have enough data, we can make more data, which is called feature engineering in the machine learning world. One of the analogs we can use for that is seismic attributes. They're very good examples of feature engineering, like dip volumes, spectral attributes, multi-scale attributes like spectral decomposition, etc. Apologize for that, lost my laser pointer there. And since I'm going to talk about what we do with neural networks, now I'll jump into introducing neural networks. And if we look at the big picture here, our inputs are seismic data, wild logs, horizons, etc., whatever it could be. And our ultimate end result is going to be some rock property or a well log we're going to estimate from the seismic data. In this network architecture diagram in the middle, we have a 2 hidden layer network. This is our input layer, and this is our output layer. You'll notice there are neurons, these little circles that are in each one of our layers. These are the actual triggers that either pass or stop or pass it weakly to the next level where we calculate the final attributes. If you look at a detailed anatomy of a neuron, it's basically a weighted summation of all the weights that come before it that is passed to an activation function, which introduces nonlinearity to neural networks, which is what makes them very powerful. And then finally, it gets passed on to the next neuron. I'll show an example. I'll show more examples of like activation functions on the next slide. And as you'll notice, the whole network is comprised of a lot of neurons. And when we're doing our learning process, we don't refreeze these layers. We freeze the input layer, so we don't need to update anything there. The only things we need to update are in our hidden layers. So when you look at a neural network, the forward pass, which is going left to right, is called inference, and also you'll hear some people call it simulation phase. And the backwards arrow, which is mainly known as backpropagation or learning, is when we actually update these weights to target our specific problem. For the inference part, we pretty much compute functions over and over until we get our final output. And on the backward pass, how we update these weights is by using the chain rule in derivation. We usually have an objective function, which is usually the mean squared error between measurements and predictions. And the gradient of that function needs to be backpropagated all the way almost to the input layer to update these weights. So that backpropagation is done by the chain rule. And the activation functions could vary. The main activation functions that were used in neural networks used to be sigmoid functions, and these days most people mainly use ReLU, which is a rectified linear unit function. And I'm not going to get into too much detail, but like these were invented to overcome the vanishing gradients problem in deep networks. If anybody's interested, you can look it up. And I'll show an animation of what the optimization process looks like on a linear model. So we have a line that has added noise to it. And as you'll see, the better we fit, the error is going to go down. And the change in this error is what's backpropagated, as I mentioned here, to update the weights of our model. And this is a very simple case where we only have a weight and a bias to be able to estimate this. In this example, you can see a 2-dimensional search space, and in practice, we actually have usually hundreds of free parameters where the search space is very highly dimensional, and there's no way to visualize that. And of course, I'm going to mention some other uses of machine learning in geoscience. And it's been proven that many machine learning methods outperform conventional methods. And the examples I'm going to point out are, for instance, fault picking, which is also called fault segmentation, estimating facies from well logs, synthetic logging, which uses artificial neural networks, and facies segmentation, where you can pick some facies manually and it gets propagated throughout your entire survey. And many of these image-based methods use convolutional neural networks, and I've seen some examples of facies segmentation using a method called variational autoencoders. So now let's talk about machine learning in QI. The advantages of using a method like neural networks in QI workflows is we don't really have to approximate the wavelet. we don't have to put any assumptions into our forward model. And we can also infer direct rock properties or logs in time or depth domain. And these are incredibly fast workflows. We can spit out a 4 or 5 attribute inversion result in a couple weeks from pre-stack data. And since we don't have to worry about a predicted wavelet, it's very powerful in ignoring distortions in the wavelet. And we've seen some examples where it helps a lot with not seeing the short period multiples or stratigraphic filtering effects on data with heavy multiple contamination. And these distortions could be due to absorption, scattering, and sometimes seismic processing puts artifacts on our data that we don't even know. But as long as it's a consistent artifact, it's going to see through it. And here's an example data set we have from the Midland Basin. It's called the Flying Dutchman 3D from Geophysical Pursuit. And we compared a conventional deterministic inversion to QEarth, which is our machine learning based inversion product. And you can obviously see the resolution increase. And this, I would like to point out that this is a blind well. And we're getting geostatistical inversion quality results in a week or 2 weeks when we work on post-stack data. And one really cool thing we can do with this is, now that it's fast, we can do it in real time. So we have a product, QEarth Real Time, where we already have a prior model that we built with our machine learning flow. And while you're drilling, we could estimate the elastic well logs using another product called QLog, where we use drilling dynamics data to estimate shear and density, shear and compressional sonics and density. And at a set interval, we could retrain our neural network model to have more data, get more data into our models, and ultimately see in front of the bit. And now I'll get into some technical details of how we do it in Quantico. And this will also be a short introduction to how any machine learning workflow is done. Our QEarth AI method pretty much takes any input that's available that's a continuous log, or horizon or seismic. We use well logs. Well, we have to make sure our wells are tied correctly, and we also have some measures to reduce the uncertainty coming from the errors in well ties. I'll get into that in a minute. And then we would want to use seismic data and any attribute that is relevant. And if the data is very noisy, the horizons help a lot with lateral continuity. So all of these data goes into mostly automated preconditioning and AI workflows, where we generate multiple realizations, and then we can generate any attribute, which is not limited to the list over here. The key starting point is input selection, where we select the seismic data and attributes we want to use. We select which attribute we're going to predict. If we have missing samples, we would want to either discard them or fill them in with a predicted version. And then we can use rock physics to generate synthetic well logs that we can place in different places in the seismic survey if we need to. And if we get the right data, it helps with faster convergence to solution, pretty much. And then all of the optimization methods in machine learning and many other mathematical optimization needs inputs to be scaled, or some people call it normalized. And we have different means to do that, where we can use min-max normalization or a z-score normalization, which is similar to removing the mean and putting the data into a -1, +1 standard deviation. And then you might want to extract more features like dip attributes or windows around the well logs for stability. And if we have a very high dimensional problem, you might want to use a method like PCA, principal component analysis, etc., for removing dimensionality, reducing dimensionality. And we have methods to automatically select the correct features and discard the ones that don't really contribute. And this is currently our R&D in progress. And then finally, we start building neural network models. So I showed you a couple examples of neural network architecture diagrams. And the selection of how many layers and how many neurons you're going to use is a critical part. And there is a method called hyperparameter optimization where you can try to find the optimal model that gives you the best result without overtraining or undertraining your model selection in your model selection process. And of course, we use randomized subsets for splitting our data to use for validation, which helps with early stopping. I'll explain a little bit. Overall, all of these methods reduce overfitting and helps with more generalized models. And typically we use shallow feed-forward networks, 2 layers or even 1 layer. You could utilize very deep networks, and we can modify the activation functions if needed. And there are many optimization backpropagation algorithms we have available, like stochastic gradient descent, BFGS, and some Bayesian methods. And another speed boost to these methods comes from GPU or FPGA acceleration. We're currently looking into options for these. And finally, after we train maybe tens or hundreds of models, we can analyze these for the performance and then group them together, which is called ensembling in machine learning, to generate an even more powerful prediction. And this also helps us generate confidence intervals of our prediction. And the way we achieve that is by bootstrapping. We take different subsets of the data for each network training, and we also start our neural network training weights at a random point between -1 and +1 on every network iteration. So we start with a lot of different initial conditions, and we make sure we converge to the same result. As I mentioned, we can take any seismic volume, any horizon, any continuous log. We use the windowing/lagging operations where we look at multiple samples around the well log seismic samples around the well log sample to reduce the errors that might come from errors in our well ties in time domain. And if in depth domain, usually the wells are explicitly tied. However, there could still be some errors coming in from delta corrections or wrong velocities where a newly drilled well may not exactly align, where we would still want to do some depth-to-depth correction to the well and or fix the seismic migration. We can also estimate geomechanical properties and even drilling data. We have done some projects where we were trying to estimate mud loss in a specific formation. And we can also get things like UCS, unconfined compressional strength, from seismic data. So what we've learned by practicing over many data environments is understanding your data and keeping it organized is key, since all of these methods rely heavily on data. And we don't want to leave any data behind. Like, for instance, there will be instances where you have a missing density log because of a washout or for any other reason. And there are either empirical or machine learning based methods to estimate these. So if we don't include these, hold on one second. I'm getting a little bit of echo. Hey, Eduardo.
I took care of it. There you go.
Okay. When we have missing data, we can use predictive models or empirical models to fill this gap, because if we're doing a model where it tries to predict certain elastic properties together, which is called multi-output models, if we don't have data in the density, none of the data that is in the same depth point will be used. So we want to fill in the missing gaps like this if we're doing multi-output models. And of course, engineering your data is also critical for quick results, which includes, like I said, calculating attributes, using physical constraints, cleaning up your data, and also somewhere where domain expertise helps is to use the correct seismic attributes. Like if you're in a carbonate play, you can use some instantaneous attributes that relate to fracturing or porosity in carbonates. Here's an example of a training convergence plot on one of our production data sets. You can see the error of our model is decreasing for our training, validation, and testing data set. And as you can see with this line here, our training automatically stopped after the validation error was not being reduced after a certain period of time, which ensures that we don't overfit the models. And I'm going to talk about this little figure here for a second. So this is from a book by Christopher Bishop about machine learning and pattern recognition, where they explain under overfitting models. And the ground truth is the green line here, which is a sine wave, and they added some noise to the measurements, and they're fitting different degrees of polynomials to this. So starting with m equals 0, which is a constant, 0th order polynomial, and then a linear polynomial, 3rd order polynomial, and a 9th order polynomial. As you can see, the error of 9th order polynomial relative to the measurement points is almost 0, but the result is completely unreliable. And also these two are, as you can see, are very underfit models. And it seems that the 3rd order polynomial does a good approximation of our sine wave in this example. So there are ways to overcome these issues where if you have a complex model, you can either use regularization methods, or you can add more data to your problem. And when you add more data, it stabilizes, and regularization allows it to have some error in the measurements where you're not exactly trying to minimize the error to 0. You will still have some error, but it will ensure a smooth result. And we usually do this by penalizing some squared weights of our neurons. So using these methods for very sparse data environments, we could still generate really good results. As I mentioned, we have done projects with 3 wells, and we gotten amazing results for rock properties like porosity, water saturation, and of course, the more you have is the better. But even with a conventional amount of data, we can get really good results. Okay, so I will now talk about some QCs we do for our final products. So keeping in mind all the stuff I just talked about, we look at some cross sections and make sure we have lateral continuity in our results. We do a lot of conventional QCs like cross-plotting, overlaying well logs. There are some machine learning metrics also we look at, like variance of the results and how much they go away from mean and the spread, etc. And one nice example here, this is again from the GPI Midland data, is we did this project for impedance with 4 wells and left 2 of them blind. And as you can see, our training wells are a really good match on a diagonal line, and our distribution shows us there's some clustering of high and low impedance values mainly, and then there's some other values scattered in between. And we see the same patterns, the same match, and a similar distribution on our blind wells. Of course, we do run into some issues when there are errors in our data. In this example, we noticed this vertical striations in our results, and after doing some analysis, we found out that there were 10 to 20 feet errors in jumps in these horizons that were a user pick error, and that's very easy to fix after we diagnosed it, and we can rerun the same model like within hours to have a final full volume. And also, I mentioned we generate multiple realizations and we ensemble them. As you can see, there's this network that's a little bit outside of the norm, and we can either manually remove those. Those networks could be overtrained compared to the others, or they may not have seen enough data. We can either remove those manually, or we have automatic ways to do that to select the best candidate networks. And at Quantico, we use genetic algorithm to, with a multi-objective function to meet some criteria and then select or discard these neural networks. And with our final selection, you can see how everything is going with the correct trend and giving us some different realizations of the rock property we're estimating. And then I'll show some generic examples from some of the projects we did. We can generate conventional attributes like impedance or density from seismic data. And one thing I would like to point out is this is again a blind well, and you can see how thin layers we result by our machine learning method. And on the density, one thing I would like to point out is we extracted density from the full stack, and it gave us very, very comparable results to geostatistical inversion that was done on pre-stack data. And the timing of these two were or in a magnitude, I mean, I think it was about from 6 months versus 6 weeks. And we got similar results in density, including blind wells. And of course, if you're not really interested in rock properties, geophysical rock properties, but you want to know your reservoir properties, like porosity, water saturation, or TOC content, we can directly infer these using the machine learning method without calculating any other attributes. And we're not only limited to these as well. I mean, any continuous log could be used. We could utilize, for instance, azimuthal seismic to estimate stresses, etc. as well. So summarizing everything, I wanted to share the power of machine learning, how they work, and how we use them, and also explain how significant your data selection and some basic understanding of data science methods are important. And finally, these will add up to generating very high resolution Earth models with a very fast turnaround, and you'll definitely make your reservoir engineers happier by giving them a really fast result from your seismic inversion.